This is a very short video about how to draw electric field lines. And so we're going to do a couple of examples here, but we're also going to do a number of examples throughout the workshops as well. So just a quick description of what electric field lines are. These are continuous curves that are drawn tangent to electric field vectors, and we'll see examples of this in just a moment. But you, of course, know that whenever I have an electric field is described by a vector field. So at every point in space, there is a vector describing both the direction and also the magnitude of the electric field. And if I just take the tangent line to all of those vectors, then I end up with an electric field line. And we'll do that in a second. It's important to point out that the closer electric field curves are to one another, this indicates the larger magnetic electric field strength. And again, we'll see that as well. A couple of very quick points. Field lines never cross. They can never cross. And if you think about this in terms of the tangent to the vector field, then this actually makes sense as well. And just by convention, we start from a positive charge and they always end at a negative charge. And they can't actually start or end unless if it's at a charge. Okay, so what I've got here is I've got two charges. This is a dipole that we're slowly becoming very familiar with. So I have a positive charge and I have a negative charge down there. And you can think about the electric field between these two charges. And what we can do is, just to get some intuition for this, we can start to build up those electric field vectors, and then we'll draw the electric field lines as well. So if I just think between the two charges, of course, there's the strongest electric field runs just between the positive and the negative charge. And of course, as I move outwards, either along this axis or outwards this way, then the electric field should be getting weaker and weaker. But always, just in that, if I'm in this plane, then the electric field should always just be pointing straight downwards. So I can see this here. My electric field vector in between the two charges is strongest, and so this is where I have the longest line, of course, the longest vector, the length of a vector representing its magnitude. And as I move away from that center, it gets weaker and weaker and weaker. Likewise, I can think about what the electric field vector is along this plane here, okay? And if I'm just sort of directly above this positive charge, then of course you know that the electric field should be pointing away from that charge. So it should just be pointing directly upwards. It should be strongest just down here, and it gets weaker and weaker and weaker. Likewise, the negative charge here, I should actually have these vectors pointing as well towards the negative charge. You remember that electric field vectors point towards negative charges. So I can draw in those ones as well. And again, this is just showing that the strength of this electric field here is strongest, and it gets weaker and weaker as you go up. And likewise down here, the strength of the electric field is strongest close to the negative charge, and it gets weaker and weaker as you go down. But this is all pointing up in that same direction, apart from this vector that's going in between the two. Okay, and I can draw, of course, anywhere else in this space, in this two-dimensional slice, of course, of a three-dimensional space. But if I, for example, take a vector out here, then of course it should be pointing out radially outwards from the positive charge. But of course, as I move further around, then this vector shouldn't quite point exactly radially outwards, because there's some influence from this negative charge. So instead of just pointing radially outwards, it'll be sort of tilted a little bit. So I've gone ahead and drawn all of these vectors in, or at least just a series of some of these vectors in, enough of them so that we can draw the electric field lines. So you can see that the field up here is pretty much just pointing radially outwards, whereas the field down here, maybe I haven't sketched this as well as I could have, but the field down here is pointing sort of a little bit towards the negative charge as well. So as we mentioned on the just previously, electric field lines are lines that are tangent everywhere to the vector field. Okay, so what I mean by tangent is they run just directly along. So if we think about the line in between the positive and the negative charge, then this just runs, there's an electric field line that, remember, they start at the positive and they finish at the negative. I've drawn that pretty badly, but I think you understand, and it's just going simply down like this, okay? Now, if I think about a line that's now an electric field line that starts, say, a little bit further up, we're going to start this one up here, okay, at the positive charge, then there's a component of this electric field here that's pointing down and across, okay? And so if I was to draw an electric field vector there, it would be pointing sort of in this direction, and everywhere I can draw this electric field vector, it has to go straight down here, and then it has to come in through the side there, okay? And this is an electric field vector now. I can do the same over here. And there we go. And that's my electric field vector just sort of in the plane. And of course, as I come further out, so I can now start my next one over here, for example, and this is now pointing upwards, but you see it gets wrapped around and it comes back up, okay? Now, my drawings aren't perfect, but I think you're hopefully starting to get the idea of what's happening. Likewise, this one comes around and goes up. And again, these all have a direction. They're electric field line. They have a direction, which means that they're going from that positive down to the negative. And as we keep coming up, you can actually see these electric field lines that start, for example, up here, are actually just going to sort of diverge off our page and go up this way. And likewise, the one up here is going to diverge off our page and just go up there. And in fact, we'd end up the one directly pointing upwards in that direction. Likewise, we're going to get some that come up into the bottom of the charge, remembering they're pointing towards the negative charge, okay? And likewise, I have these. So there's a lot of things that you can see going on here. This is what it looks like for an electric field vector, albeit probably better than how I've drawn it here. It should be. But you can see now, you can start to get a feel for when there's more electric field lines, and if you sort of equally space where you start these electric field lines, then if there's more electric field lines, then the stronger the field is, a stronger field is represented by the density of these lines. So you can see I have this dense field in this region over here, there's dense field lines in the region over here, but I have a lot of field lines. Whereas as I move further out, if I'm up here, there's only really one field line, and the field is a lot weaker out at this point. So this is the electric field around a dipole and this is sort of how to draw it. We're going to do, as I said, more examples throughout the lectures or throughout the lectorials as well. I just want to do one more quick example for you, and this is because we're going to discuss systems like this quite a lot, but this is essentially a parallel plate capacitor, and if we ignore the boundaries, and what we sort of always think about with parallel plate capacitors is that we have this line of charge, or actually a plate, this is sort of extends in and out of the page for us here, but we have this plate of charge and a positive charge and a plate of negative charge, okay? And if you think about this, that the size of the plate here is much longer, is much bigger than the distance between here, then essentially this is an infinitely large plate. And when you have an infinitely large plate, again, we'll discuss this more in detail when we talk about capacitors, but of course you can see that the field lines here, they must just go from the positive plate to the negative plate in such a way, okay? And you can draw these field lines all as such. And one thing that you can notice straight away if you've drawn these in a reasonable way is you can actually see that there's equal spacing everywhere between these field lines, okay? Obviously, you're going to get edge effects that are different here, but what we're assuming now is that the size of this plate is basically infinite, so this extends infinitely far down and infinitely far up. But so what you can see is the distance between any two field lines is the same on this side as it is on this side. And if you think about that a little bit more, what it means is that the electric field in between these two plates is constant, okay? So it doesn't actually change moving from one side of the plate to the other. And this is something that we're going to explore mathematically, and we'll be able to derive and show mathematically very shortly.